Alright, so today's selected question is 721 accounts merge. We are given a list of accounts, each element accounts I. So each account in this accounts is a list of strings. So that the first element of this account is a name and the rest of the elements are emails. We would like to merge these accounts. Two accounts definitely belong to the same person if some email that is common to both accounts. And note that even two accounts have the same name, they may not belong to they may belong to different people, as people could have same name. So it's the emails that we can use to connecting those dots. It's not the person's names. And a person can have any number of accounts initially, but all of those accounts have the same name, so we don't need to worry about the email being shared by two accounts that have different names. We don't. So this is just telling us we don't need to deal with that case. After merging the accounts, return the accounts in the following format. The first element is still the name. The rest of the elements are the email in sorted order. And the accounts themselves can be returned in any kind of order. The example here we have John Schmitz, John Bravo, John Schmitz. So this email and this email are the same. We probably need to consolidate these two accounts. John New York and Mary John 00 and John 00. So John has a lot of accounts. John Bravo, John Bravo. So the result is Mary only have one email. John Bravo, it's just the same person. This is appeared how many times? Twice, but it's the same account. But this John Bravo is the different John because there are no email shared between this. And then the last account is a John with 3 different emails. So just imagine that you have all these emails, and you can sort of like thinking. When you see two emails appear in the same account, you can try to connect those emails, and in the end you just try to identify how many connected components in the graph that you have. And for each of the component, you just use the name, shared name, username, and return a list of connected components with the names and sorted emails. So yeah, this is pretty much a connected component graph problem, and in which you have to find all the connected components. So for this kind of problem, finding connected components in graph, it's generally better to use a union find algorithm, which I learned in the algorithms class from Princeton, the Coursera online course. I did not go to Princeton. I think it's a very first week's lesson. It's like 6 years ago, but never really used that outside coding questions. So I forgot a lot about that. If I coded it about right now, I might have a lot of problem. The other method of doing this is pretty much DFS. You still have to build out some kind of adjacency list. So you can treat this graph as an undirected graph, and just try to build out the adjacency list first, and then to memorize the version of DFS. You starting from email and try to go to the next email that is connecting to it, and then goes to the next email that's connecting to this one, 00 here. Which one would it be? John New York. And after you have visited all the emails you can visit based on the graph, you know that you have exhausted the connected component, the nodes on the connected components, and then after that you basically detected the components as well. Just remember you have to collect all the emails in the beginning and memorize which one you have visited. And once you do a DFS, go back to check the other emails that you still have to work on. So that would be the first code I will code up. Basically, build the graph and then do DFS. The time complexity for this is pretty much going to be building the graph is going to go through all the email at least once. So if we have a big N number of different emails in here, occurrence of emails, building the graph, it's pretty much going to be that. Note that we actually don't need to build the whole graph. As long as these two emails are connected, we're fine. So if the account has 3 different emails, like this one, we don't actually need to build the how many different pairs of the edges we need. We can connect this John 00 with John New York and connect John 00 with John Smith, and that will be enough. Unlike building out the complete graph, in that case we will actually connect John New York with John Smith as well. If we actually build out the complete graph, the graph building is quadratic because we have to visit every possible pairs of the edges. That would be a little bit worse in the time complexity, at least in the graph building part. We only need to connect, just to loosely connect this email, so that as long as these three emails are in the same component, we are fine. We are fine for this problem's purpose. We don't need to actually build out the complete graph. So if we just connect every email with the very first email in the account, that will be a linear time complexity in building a graph. Then is the DFS. We are pretty much visiting every email once, so that's but the problematic part is the sorted order thing. So just assume that after we figure out the final accounts, and on average each of these accounts have like k different emails. Yeah, let's just say that on average different every account has k emails. Sorting this k emails will be k log k, right? And so yeah, there is a log elements in the time complexity if we return the thing in the sorted order. Yeah, so that's pretty much roughly the time complexity. For space, we're pretty much just storing all the emails, so that's linear with respect to the inputs. So let's code this thing up. So for the first step for this question is to build out an adjacency list, the representation of the graph. Lists. So this adjacency lists is doesn't autocomplete. It's a dictionary with the key will be an email, and the value will be a set of other emails. So that's just how the adjacency list works. For account, in the accounts, email. The very first element is the username and the person's name. The email is in the is the elements from the first and on, from the location 1 and on. So we basically populate this adjacency list by connecting emails with every other email with the very first email. So so since it's undirected, we actually use two directed edge to represent that the fact that the edges have no order in it, so just duplicate the number of edges. We can also keep track of the email to name mapping. So in the end, we can, when we populate after we find the components, connector components of emails, we can still grab like a label to that components, which is the name. And name is the very first element for that account. So for this, we also initialize a dictionary for the purpose of this email to name mapping. So that's the first part. So if we have let's say that every person have AI different accounts. So the time complexity for building out this is actually so you can see that for each of the account, we basically enumerating over all the emails. So let's say that we have each account has AI number accounts emails. This would just be sum sigma. So this is the both the time and the space complexity for this graph building part. And then we do DFS. Okay, so we use a hash map, hash set to keep track of the emails that we looked at, so that we don't visit the same email twice. For email in the emails are the keys to the adjacency list. So we don't visit the email twice. The stack is initially to be just this email, and we will collect the components and put that into account, I guess. Let's call it all email. So this is a for DFS we're using a stack. BFS is using queue. DFS is append the stuff to the right and immediately pop that out. So that we always go further and further before it so we go as far as possible, then backtrack. That's pretty much just DFS. So we will try to visit all the alternative, the emails in that component here. I need to also keep track of this this email here. Memorize this one too. So it's add, not append, because visited is a set. Okay. Okay. So after this DFS search, we will basically find all the alternative emails for this particular person. I blocked the view. Sorry. Yeah. So let me actually just finish the code and talk about that. So we append this append the name as the very first element, and we also have the emails for that person sorted. Okay, so the just talk about the code. The first step is to build the graph by the adjacency lists. It's an unordered graph, so we have the bidirectional links in there. So for each email in the account, you are pointing to the very first email, and the very first email is gonna pointing to that particular any other emails in the account as well. So the reason for this is just trying to just make sure that the email that should belongs to the same connected components can be detected by with respect to using this adjacency list, using this graph. And we also noted down the display name for the emails. In the DFS part, we just gather the connected components and put a name tag onto that components. In the end, we return the we collected the name tag and the sorted emails. So that's pretty much the strategy. Okay, so let me actually yeah, maybe change this to emails. It's a little bit more readable. Let's quick check if there are any problems. We have a set to keep track of the emails that we traversed, basically the nodes in the graph that we traversed over. For each of the emails in the adjacency list, if it's visited, we skip that. Otherwise, we memorize the node that we visited and try to start a DFS search from that node. And the way to do that is using a stack. We pop out emails and try to explore the neighbors of this particular email, the node, and we go as further as possible, and then if necessary backtrack. So I don't see anything that's obviously wrong, but the thing you can see here, it's pretty much this thing too. If you only look at the outer loop for email in adjacency list and the stack here, if there is no such line here, the time complexity will also be this. But since we have sorted here, so it's pretty much AI log of AI. So that's the time complexity. So let's try to submit this. Okay, it works. So this is the DFS solution. We'll talk about the union find solution, which I'm not sure if I can pull it up. If I couldn't get it working, I'll just cut the video. So yeah, so for union find, basically it's we use a fixed size array to use integer numbers in the array to indicate the parent of the node, basically. And when we insert a new node into there, into a pair of node that we need to connect. So we have two emails. We need to identify sort of a node that these two emails belongs to the same person. We just union them. How to say that? Yeah. Let me try to code it up. Actually, I'm rusty on the memory. So the union find is basically all depends on this union find data structure. Let's call it union find, which is a class. We have to know the number of nodes that we're gonna try to connect right ahead of time. So initially the array, it's every node is its own parent. You can think of like that, and so the location, the cell value for the node I, it's pointing to its parent. You can that's pretty much how it is. Or you can think of like a cluster centers. Yeah, if you know about machine learning clusters and stuff. So when you have a cluster of nodes, which is in this context is connected components, you just have a center or center node. That's the node in the cluster that sort of like a team leader sort of thing. The array here, when you look at the ID's I, it's going to pointing to the cluster center that containing that node. So initially, every node it's its own cell, it's its own leader, and when we're connecting the two nodes together, we'll update one of the nodes ID to be the leader's node ID, so that through time, when the cluster begins to form, we're gonna have more nodes that has the same ID number, the cluster identifier. That's basically how the IDs works. So to find the node with ID I, we just try to go through the array by jumping, trying to find the leader, and if the leader has another leader, we try to go to that until the leader points to itself. Yeah, I'm already the leader, so I'm telling the other people that the outside world, I'm leading my team. That number is the one that we return using this find operation. So we will, if the node is not directly reporting to the leader, it will also trying to tell its directory report. We need to both pointing to the leader directly. So that's what's called path compression, I believe. And then what we do, so these two lines basically do the path compression. So if you ask someone who is your leader, not only you can return that leader number, you can also tell the people that you direct into, you change all those to the ultimate leader throughout this operation. And union is basically put two nodes into the same cluster. An optimization that we can do is to memorize the size of the clusters, so that when we actually do the merging, we can always merge the smaller cluster into the bigger cluster, so that so that the sum of the I think the find will be more optimized if we just keep track of the size of the clusters. But I may screw it up, so I'm not coding that part. Maybe some other time when I do the union find problem, I will code it up. I need to refresh myself. Yeah, so this is the union find operation. Basically, the strategy is to go through the emails. If they appear in the same account, we try to union them, and in the end, we just for each of the email we find their cluster leader, and we as long as two emails have the same cluster leader, they must belong to the same account, and so that by that way we can reconstruct the desired accounts and just stick a username to it, so a person's name to that. So that's pretty much the strategy. So we'll still need to maintain an email to name mapping, which is a dictionary, and we go through the accounts, at least the ones, to form to construct this mapping. And since this union find algorithm is using the index using node ID integer node IDs, so we have to have another thing that's the email to unique email to integer identifier mapping. We need to create that as well. So we basically can since the emails that the unique emails is basically the keys to this dictionary, we can get that using this mapping. Keys. And the required n number of nodes in the constructor for union find is basically the length of this thing. So after this, we will just use union find to connecting those components. Again, we basically only need to connect every other email in the account to the very first one. And we are not union the email strings, we actually union the IDs for each email. So by doing this, we can pretty much you know, group all the emails into their clusters, and so that we can query the leaders to know that whether two emails belong to the same account. So then we try to reconstruct the result. How do I call it? Let's just call it emails. So each let's call it clusters. So basically, this is going to be the mapping between from the cluster identifier, which is the team leader, to its individual reports, group of members, sort of thing. For emails in so for email in this these clusters. Find email, which is the cluster ID for where this email belongs to. So that we're using ID as well. Yeah, so this is the integer class ID for the emails, for the cluster or the connected components that this email belongs to, and we append the email to that ID. So by this for loops, we basically have all the gathered all the connected components. Then it's just to reconstruct the solution. Something plus the sorted emails, and this is gonna be the name, which is actually I deleted the O code, so it could be any email, doesn't matter. Just for convenience, put 0 here. You can call this reconstructor. Or actually call it, constructor merged accounts. So yeah, this this will be the code to use union find to solve this problem. So again, at top level, what union find is, you initialize the n number of nodes, each is its own leader. In the union operation, you basically connecting the two nodes, and you assign one of the leader for the cluster, for the node where the node belongs to, into the other cluster's leader. So basically, so it's merging two connected components into one bigger one. And for this find operation is to basically, for any given node, you try to find the leader for that for the connected components that the node belongs to. So with this data structure, we can solve this problem. Here we construct, we're basically building out some auxiliary helper stuff. That's two hash maps, email to name and email to the integer ID, so that it's required by the union find. And in this double loop here is the union operations. Even though it's a double loop, it's actually linear with respect to the number of unique number of emails. So, and it's asymptotically. There is a function, big A function. I forgot that, but it's complex the mass, showing that it's roughly linear. So this solution will actually be slightly better in terms of time and space complexity, compared to the adjacency list plus DFS solution. I guess I would have problems code this up. I might have a problem here. It looks okay to me right now, but under pressure, I'm not sure if I can pull it off. Yeah, let's give it a try. I think it's working code. Okay, about the same with the adjacency list and DFS. So yeah, again, that big A function is just approximate. So with relatively small problem size, I guess there's not much difference between this one and the DFS one. So that's the question for today. Yeah, be safe, everyone.